talk about the transformer-based 3D point cloud semantic segmentation, and our group members are Gu Zhexuan, Lei Siyu, Liu Fan, Ouyang Zhixing, and Shanu Yao. In the first part, let me introduce something about the technology. Realizing effective 3D scene understanding is one of the key problems in the field of computer vision. Comparing with the major 2D detection technology, 3D detection is more challenging and have a lot of aspects to develop it. In recent years, significant progress has been made in the understanding of 3D point cloud, and good results have been shown in various tasks. We present an improved approach for semantic segmentation and point mask prediction on 3D point cloud based on 3D bonnet. Our approach follows the per-point multi-layer perception design philosophy and comprises a backbone network followed by semantic segmentation network and the point mask prediction network. Instead of directly using MLP slowly, we introduce an improved self-attention mechanism to extract global features. The improved transformer-based model directly predicts the semantic label for each point in the point cloud, while also generating a point-level mask for each instance. Our extensive experiments show that our new model outperforms the original 3D bonnet. Secondly, I want to show something about the 3D bonnet. The overall framework of 3D bonnet is shown in this figure, which is mainly composed of instance-level bounding box prediction and point-level mask prediction. As the name implies, the bounding box prediction branch is used to predict the bounding box of each instance, and the mask prediction branch is used to predict a mask for the point in the bounding box. In this branch, we fuse point features with each bounding box and its score, and finally predict a point-level binary mask for each instance. Transformer with attention mechanism have emerged as a prominent concept in deep learning research, owing to their ability to significantly enhance the performance of various tasks. In the third part, we modify attention operation proposed in point transformer paper. We first let the layers labeling points of each point in the batch of K and N. Then change the original calculation of score using K transpose time Q to K minus Q. And then add the position encoding information of the relative layers point. And then go through the mapping function gamma. Here we use the MLP network with two linear layers and an activation function network. The same operation is performed for the same V. And we also add them with the corresponding position encoding for adjustment. The computed result is subject to a normalization operation on the columns. Here we use the softmax. The figure demonstrates the base structure of our model. First, we use FPS method to help us ease the limited GPU memory problem. Secondly, because of the spatial imbalance of point cloud dataset, it's not suitable to directly apply convolution operation on it. Thus, MLP becomes our first choice to extract useful feature. In the first stage, we use MLP, which comprises two cascaded feed-forward LBR blocks to embed the lower dimensional point feature to the high dimensional space, which contain more useful information. Due to the constraint that we have introduced before, only sample points participate in self-attention. We adopt a very naive way that those points which don't take part in the attention only have a domain feature filled with zeros. After summing up Phaeton and F, there are another two LBR blocks to integrate all feature vectors. To extract global feature from point cloud, we must consider some properties like rotation invariance and translation invariance. That is to say, the point order should not affect the global feature. Therefore, maximum and average are used frequently in global feature extraction. And we eventually use max function. In the fourth part, we evaluate the model from three parts. Firstly, we compare the result of the 3D boundlines and our model on some object categories. As the table and figure show here, we can easily find out that the accuracy of our model has improved, which verifies the improvement of our model. Last, figure here shows the specific object accuracy prediction on each epoch. Then, we compare the result of 3D boundlines and our model predicts on the office room with different objects. Different colors indicate different semantic labels. In conclusion, our model performs perfect. Thank you. In the end, we record a video of the result of our model on 3D point cloud semantic segmentation.